A skydiver has the time of their life. A cat survives a 380-foot fall, an astronaut drops a feather and a hammer, and a guy who jumps from almost space travels faster than sound. What do they all have in common? They are falling. But if gravity pulls on everything the same, why does falling look so different for each one? Well, falling just means one thing, that gravity is pulling you down. That's it. Gravity doesn't care if you're a bowling ball, a piece of paper, or a slightly terrified human. Gravity pulls everything on Earth at the acceleration of 9.8 meters per second squared, which is simply called g. And another way to look at g is that it's the strength of the gravity you feel. Sometimes while doing maneuvers, fighter pilots will feel up to 11 g's or 11 times Earth's gravity. So if gravity treats everything the same, what is causing all the falling chaos? Meet air resistance. Now, air hates being ignored or shoved out of the way. And the faster you fall or the bigger you are, the harder air pushes back. It's basically nature yelling, "Hey, slow down!" So falling becomes a tug of war, gravity pulling down while air resistance pushes up. In science, we use arrows called vectors to show the strength and direction of these forces. And whoever wins decides what happens next. On the moon, there's almost no air, so no air resistance. So in 1971, when astronaut David Scott simultaneously dropped a feather and a hammer, they fell with the same acceleration and hit the ground at the same time. No magic, no trick, just gravity doing its thing, with zero air interference. You can do something similar at home with a piece of paper and a book. Dropped separately, they fall at different speeds, but take away air resistance by placing the paper on the book, and voila, it's a little bit like space. And if you noticed how slowly the hammer and the feather fell, it's because g on the moon is 1.62 meters per second squared. That's 1/6 the acceleration we have here on Earth, which is neat because on the moon, a person would weigh 1/6 as much as they do on Earth. If you're 200 pounds here, you're just 33.2 pounds on the moon. This is because your weight is your mass, or how much actual material makes up an object, times g, the acceleration due to gravity. So when g changes, your weight does as well. Whoa, how much would you weigh on Jupiter? And now for a science history fact check. In the late 1500s, Galileo Galilei discovered that objects accelerate equally when falling. Rumors were that he did this at the Leaning Tower of Pisa. Well, while he did do extensive experimenting on gravity, there is no evidence that it was at the Tower of Pisa. Still, great job, Big G. And if you want a detailed breakdown of the science and math that explains everything you're seeing, go to the last chapter of this video or just watch until the end. Now, what happens when a person is falling and there is no air? Well, the Austrian Felix Baumgartner set out to find the answer back in 2012. He took a balloon ride to the stratosphere. Here he is, above 99% of Earth's atmosphere, and then he jumps. Now guess what happens next when you have Earth's gravity but no air resistance pushing in the opposite direction? I suggest watching that video. It will make your heart skip a beat. So when Felix first jumped, gravity was pulling down hard, but air resistance wasn't doing much of anything. He kept speeding up until he broke the sound barrier, like a fighter jet. But as he fell lower, the air got thicker, air resistance increased, and eventually, gravity and air balanced out. And that balance has a name: terminal velocity. It's when you stop speeding up because air is pushing back just as hard as gravity is pulling down. For normal skydivers, that speed is about 120 miles per hour. Felix topped out at 843 miles per hour. Change your body shape, however, and you can change how fast you fall. Which brings us to cats are well known for surviving falls, even from tall buildings. But this isn't by luck. Here's their secret. First, they use their agility and flexibility to get their feet below them. Second, cats are different from humans in that their terminal velocity is half of ours, 60 miles per hour, which they reach after 50 to 70 feet of acceleration. When they stop feeling the acceleration and their speed is steady, they relax. They spread out, arch their backs, and create more air resistance. They're basically tiny little furry parachutes. And cats aren't breaking physics, they're using it like pros. Now they still get severely injured with high falls, they just tend to survive them. But there is a safer way to fall. A common misconception is that there is no gravity in space. But astronauts at the International Space Station have almost the same amount of gravity as people on Earth do. Gravity is pulling them down, but the space station is also moving horizontally really quickly. The result is that they fall, but they constantly miss the Earth as they do. Now, Sir Isaac Newton explained it this way. A cannon on top of a mountain, shot at slow speed, the ball will fall to Earth. Speed up the cannonball, it will go further but still fall to Earth. But once it is fast enough, it falls, just missing the Earth. So astronauts aren't floating, they're actually falling at a constant speed that just feels like weightlessness. And this feeling of weightlessness can be recreated for training purposes on the Vomit Comet, an airplane that NASA uses to dive at a specific speed and angle to give the passengers the feeling of weightlessness, or zero G's. So on the moon, gravity works alone, and Felix had thin air. Skydivers have plenty of air, cats max out their air resistance, and astronauts, well, they just endlessly fall. Same gravity, different air. And that's the whole secret. Or is it? And finally, here is the science and math behind falling. Gravity and falling have a dirty little secret. Heavier objects actually do have more gravitational force than lighter ones. So why do the hammer and feather fall the same on the moon? Well, because the hammer, being heavier, also has more inertia, or desire to stay still. It takes more force to get it to move. Here's the math. Gravitational force is the object's mass times g, gravitational acceleration, and that is equal to ma, mass times acceleration. This is Newton's second law of motion. The mass, big or small, always cancels out because they're on opposite sides of the equation, leaving acceleration of the object equal to g. And remember, g is different depending on the mass of the object. And on Earth, this is different because there are more forces involved, like air resistance. So how fast an object accelerates when it falls depends on how big the air resistance force is compared to the gravitational force. The bigger the difference between air resistance and gravitational force, the faster the object will accelerate. If you drop two balls, the same size and the same air resistance, but with different masses, you can see that the more massive ball accelerates faster than the lighter mass ball. Science is so cool. I hope you enjoyed the video. If so, please give it a like and subscribe to the channel. And until next time, stay curious.